Great. Hi, everybody. We've reached the top of the hour. So welcome to everybody. Hi, everybody.
Hello.
Hi, hello to everybody in Georgia. And welcome to our second workshop. And what we're going to be doing today is we're going to be going through the results of our experiment that we conducted over this last week. And we're going to have a look at another experiment. And then if you like, I'm very happy to stay on a little bit afterwards. Maybe some of you have got some challenges with connecting to the dashboard, whatever that may be. But we don't have to rush that because we've got plenty of time to connect to dashboard, etc. Because we're not going to necessarily be needing it for this experiment that we're doing this week. But it would be nice if we could have it for next week. I would really, really like some feedback on who was able to do the experiment and what did you notice? And let me just repeat the question. What we were looking for is there a relationship between natural light and temperature? Dr. Cassie, I was just wondering, did anybody from your class be able to conduct that experiment and maybe we have some feedback?
Actually, because this is a different fourth grade class, so
okay.
We haven't done it with this class yet. Every week I'll have a different fourth grade class involved and a different fifth grade for the first few sessions, but we have it. We're getting ready to start it when we get back from break because next week we actually have the whole week off. So they are
great.
Fourth grade is starting all of the experiments.
Okay, absolutely wonderful. Absolutely wonderful. Okay, so what I'm going to be doing then is I'm going to be giving you a little bit of a sneak preview in terms of the results that you would achieve. Cameron, do you have any feedback? Jim, were your students able to do anything?
Yes, my students were. They were able to do natural. Most of them got everybody got natural light, the temperature and the UV. Some groups got to do the UV and the UV comparison between natural and artificial light with the temperature. And they posted their results to the Discord.
Oh, fantastic. Okay, that's great. So
yeah, the preliminary, we didn't have time to like really make it look nice or anything because we ended up with a half day, messed up week, but that's okay. Also next week, they will not be here because it's break. So we'll just be participating. They'll pick up asynchronously the next following week.
Absolutely, absolutely. Great, that's absolutely wonderful. And yeah, that is the right place to post it. You know, to be able to share it with everybody. Yeah, absolutely.
Andrew Jakes is one of the students upstairs right now.
Okay, great. Hi, Andrew.
Well, I'll speak for Miss.
Yes,
I'll speak for Miss Bailey's class. I have their rough data with me, but they practiced indoors with the sensors, and then they went outside. I shouldn't say they went outside. We placed the sensors outside and then brought them back in. As for their analysis of it, they haven't given it to me yet. I do have their rough data. And they looked at the sensors and wrote it down so they could practice. Mm-hmm.
Yes, absolutely. To look at the screen and then write the data from the screen.
Yes, that's what they did. Yes.
Absolutely. So that's absolutely perfect. What I'd like to do is I'd like us to actually go through a little bit of the theory in terms of how is it that sunlight actually affects the temperature of the atmosphere. So I've prepared a few slides here. So let's just go through those. Jim Tyson, you know a lot more about this topic than I do, so I was just wondering if you wanted to chip in. Also, you're very welcome just to interrupt me and contradict me and say, Judy, the water obviously goes around the other way in your part of the world.
Uh, I would prefer not to contradict you as much as possible, but but I'll be happy to share anything I know.
Absolutely, and yeah, really, and also please, you need to make sure that that yes, that I have it right, if that's okay. Great. So last week we had a look at which sensors we had in our kits, and what we've been doing is we've been working with our light sensor, and we've also been working with our weather sensor to get temperature. So let's see where we let's understand a little bit more about light. So light is radiated, and if we have a look here. This is, it's represented as maybe a sun, but let's actually say that perhaps that is a light bulb, or otherwise it's a torch, something like that, a light source that's a lot closer to us. If we move 1 unit away from that light source, so we could say maybe it's a yard, maybe it's a meter, what we find is that the rays, the light rays, or the light beams, what they need to do is that they would light an area, a flat area at right angles to it, perpendicular to the rays, and we could say that that would be 1 square, whether that is a square yard or whether it's a square meter or square foot, something like that. If we were to move now 2 units away, then what it is that this square, the area that it needs to cover is actually now 2 by 2. So we know from mathematics that 2 times 2 is 4. So now we've got 4 square units that needs to be covered by the same amount of light. So what we can do is we can say if our light intensity was 1, when it was 1 square, then when it's 4 square, and we've got the same amount of light, then it's 1 divided by 4, so it's actually a quarter. Now, if we move 3 units away, now this becomes 3 by 3, which is 9 square yards or meters, and we've still got that 1 unit of light. So now that intensity becomes a 9th. So you can see here that as we move away from our light source, it's not actually linear. What it is it's actually exponential in a way, but it's inverse exponential. So what we have is we have a unit of 1, then a quarter, then a 9th. So what it does is we can say that our light intensity is the inverse square of the distance from the light source. Okay, so it's inversely proportional, but the thing is it's inverse to the square of the distance, because we're having to square the distance. Jim Tyson, am I correct with that?
Yes, you are. It's called the inverse square law. It's 1 over the distance squared.
Fantastic, great, thank you. Does anybody in the room have an idea of where there's another case where we can use the inverse square law? What other equations do we have an inverse square law? Okay, gravity. The force of gravity is also the inverse square to the distance between the objects. So when we're in space, when we're considering objects in space and the gravitational forces that they impose on each other, I'm not going to take it personally that everybody's leaving the room. It must be that the bell went. So yes, and the thing is that what we're looking at here is we're taking everything that we're learning through this process and we're applying it to what would happen when we're in space. What happens when we have hardware in space? So the further our satellite is, the higher our orbit is, or the further that our satellite is away from our planet Earth, the less the force of gravity according to the inverse square law. But we'll cover that in a much later section. So let's actually have a look at natural light. So it doesn't only comprise visible light, sunlight. What we have is on the high energy extreme, what we have ultraviolet light, and in the lower energy area, we have infrared light. So if we were to take, and you can see here that it's not a straight line. What we have is we have the number of photons that we're receiving, and the photons are really actually the packets of energy in terms of light. And here in our top right-hand corner, we can see here where we've got wavelength in nanometers. The longer the wavelength, the more it shifts to the red and also into the infrared, which means like beyond red. And the shorter the wavelength, the higher the energy is, then we're into the ultraviolet zone. So it's also before violet. We can see that ultraviolet is also divided into 3 waves. Okay, we have relatively long wave, UV, which is UVA, referred to as UVA. Then we get the middle wavelength, which is UVB, and then the short wave, very short wave, very, very high energy UVC. And so that is really, if we were to classify our light wavelengths as well as our ultraviolet wavelengths, we would have UVA, B, and C. And how does this actually affect our planet? So we can see here from this graphic that the UVC, which is the most dangerous because it's the highest energy light, actually gets trapped by our ozone layer. So our ozone layer is anywhere between it's around about 20 to 30 kilometers. So how much is that? 20 kilometers multiplied, that would be 60,000 feet. Yeah, multiplied by 3. Yeah, so around about 60,000 feet above sea level, we would have our ozone layer, and that actually protects us from the UVC light. What it is that the ozone molecule itself is 3 oxygens, not 2 oxygens like the normal oxygen molecule that we breathe, but ozone is 3 oxygen molecules. And it's actually only at that altitude where it's stable. So that is why it sits there. It doesn't get destroyed at that altitude and at that atmospheric pressure. And the thing is that what we find is that those 3 atoms, those 3 oxygen atoms, vibrate at a particular wavelength that really suits UVC. So what happens is that the molecule is able to absorb UVC because of those particular bonds, oxygen to oxygen bonds in the ozone molecule. Some of the UVB does get through to ground level. And we can see on the right-hand side here that UVB is more dangerous for us. And then we have the UVA. A lot of that does get through, and it can be blocked by pollution and smoke and water vapor, etc. And what that does is that gives us the aging and the wrinkling. So the UVA is not as dangerous for us, but certainly they come in the same package. So the UV index. The UV index, what you can do is you can Google it and you can look up the formula for the UV index. But what it is it's a factor, and it's a combination of UVA and UVB. A certain portion of UVA and a certain portion of UVB gives us our UV index, which is then an indication of how dangerous it is for us to be out there. So that explains a little bit about UV ultraviolet light. And now what about the infrared light? So this is not to scale. We can see here in this artistic impression that we have our sun, and the rays from our sun are also have that infrared radiation. And what happens is that as those sun's rays come through our atmosphere, quite a lot of a fair portion of that infrared is absorbed as heat in our atmosphere. Also, when the light is reflected again, there's more absorption. So the thing is that where we have areas like where we have deforestation and desertification, what happens is that those dry deserts, they eventually become very sun bleached and they reflect more of the light rather than absorbing it. Also, there's not enough vegetation to absorb the energy from the light and convert that light into food using photosynthesis. And so what happens is then we get the reflection of that light again, and then we get more absorption. So that is why it's almost, we have this like snowball effect with the warming of our atmosphere, because the more greenhouse gases we have, the more energy from the infrared can be absorbed, etc. So that is why we get this runaway warming, and it's this as well. It's not linear. This is also, you know, exponential. So what we need to do is we can't control, and we don't want to control the amount of energy that we get from the sun. What we need to be able to control is have it reflecting less, and also we have to make sure that we reduce our greenhouse gases so that also that energy doesn't get absorbed. Those are two things we actually can do something about. So the thing is that what we find in our experiments is that when we're in full sunlight, not only are we receiving the visible light, which is being it's being represented by the lux value on our kits, but and we're also getting some ultraviolet, which we're seeing in terms of the UV index. But what we're not seeing here is the infrared. We're seeing the infrared in the increased temperature, because that's what infrared does. What it does, it's an indication of temperature. Does anybody want to? Let me actually stop at this point. Does anybody want to share anything that they know about infrared, and how do we detect infrared? How do we use infrared?
So police cars and like fire trucks use it.
Absolutely, Andrew, you're very right. What it is that we can have infrared goggles, we can have infrared cameras or sensors, and usually what we would do is we would use that as a for a heat signature. What we can do is we can have a look for wildlife going through forests or wilderness areas. Also, we can track human beings because we can see the heat in terms of infrared being reflected. Yes, certainly a firefighter is needed, because very often they think that the fire's been put out, but in fact it's still smoldering somewhere, maybe underground or something like that. So they definitely use infrared cameras for that. And police as well, if they want to see how many people there are in a building, something like that, before they go in, they want to be able to see that. I can see there's something in the chat. Great, Dr. Cassie, that was absolutely fine. Yeah, and then Richard, yes, absolutely. Heat loss in buildings. Yes, we use infrared lamps, and often in a restaurant or sometimes in a fast food joint. What they'll do is they'll have the pass, which is that stainless steel tray that they put the food on, and then under at the bottom there's actually infrared lights which are shining, so infrared heaters which are keeping the food warm. So yes, we certainly do. We definitely utilize infrared for heating, but also we have infrared sensors that can detect heat. Yes, Jim, absolutely. Yes, remote controls. Yeah, it's a nice form of light energy to use, because we don't want to use infrared or something like that, or laser or anything like that, because that's way too high energy and dangerous. Dave, by the way, hello, welcome. So welcome to our session. So what I'd like to do now, so I think that when everybody does the experiment, they should notice that as the natural light intensity increases, that the temperature also increases. You may find that it's not a straight line. You may find that it is a slight curve. The thing is that when we talk about natural sun, we're talking about sunlight, and we're already so far away from the sun that any little bit of distance is really, it's not going to be detectable at all. So great, Dave, thank you. You with Jim and his students, so great. Once again, welcome. Hello, hi, lovely to see you.
Hey, Judy, I have a question.
Yes, please.
So you had some really nice graphics on the layers, some of the layers of the atmosphere and the UV lights that they absorb or that can get through, let's put it that way.
Yeah.
Which layers is the rocket and our instrument going to pass through?
Okay, I'm going to share my screen again so we can just go back to that. Right, so our experiment, our rocket itself is technically going into space. So I actually had a brief call with Blue Shift Aerospace today. So we're definitely looking at higher than 100 kilometers, hopefully considerably higher. So that is, yeah, excuse the sun being so close here, but it's also not to scale. But certainly what we're going to be doing is we're going to be completely free of these layers. So our experiments will be exposed. They will be exposed. So
excellent. So we could actually, yeah, we'll be traveling through all of them. Plus,
yes.
you know, you could come. So technically, I guess, not knowing the setup, but you could actually compare the UV levels.
Oh yeah.
Oh, that's
definitely. That is definitely going to happen. Jim, what we have is we've arranged with Blue Shift Aerospace that we're going to have a window. We may actually be lucky enough to have almost a transparent layer in the rocket. So a number of the payloads are going to be able to have access to that window. So when we get closer to the time, I think what it's going to be about is it's going to be about collaboration between the different groups to say, you know what, our payload is going to have access to the window. So we will collect the light data and we'll share that with you. Others will be in this closer to the center, and they'll say what we're going to do is we're going to monitor maybe temperatures. Maybe, you know, it'll be better for them to monitor vibration because they'll be in the center, you know, in the core, that kind of thing. So yes, absolutely. We're going to have wonderful opportunities to be able to say who's going to focus on which data set, you know, to make sure that we do it fully. There's also
better and better every day. Like,
right. Oh, thank you. Thank you. Your check's in the mail. Your check's in the mail, Jim.
Yeah. No, this is great. Thank you very much.
Absolutely, absolutely. And I think, you know, on that, in terms of the UVC, we've had another development over the last week in terms of our flight hardware. The team, originally what we were going to have is we were going to have, let me just do it this way. Let me just pull it apart. originally what we were going to have is our core unit was going to be, it is, and it's still going to be 3 chips long. Okay. And what we were going to have, what we're still going to have is we're going to have the same core as we have here. So maybe I should just use this one. We're going to have exactly this ESP32. So we're going to have the same core. So any of the code that we developed through this entire program, we're going to be able to use on our flight hardware. So you're actually going to find that you're redeploying these kits as your flight hardware, as your engineering models to develop the code and everything else. So the one module is going to be the same core. The middle module is going to be it's going to have an SD card. So there'll be an SD card interface. So we can have an SD card, and so we can save our data on our SD card, as well as transmit our data using I2C to another memory source, as well as the radio functionality and the downlink being provided with the rocket. And then the third chip was going to be a LoRa radio for those groups who wanted to maybe use it on a high altitude balloon or for remote sensing or something like that. What it's going to be now is that the LoRa radio is actually going to be detachable. And what you're going to be able to put on instead is going to be an interface for analog sensors. So the students can actually build their own sensor block with analog sensors. And UVC sensors, most of them that we find that are affordable and that are supported with code, etc., are analog. So what's actually quite great is that we may find that some of the student groups actually want to develop a UVC sensor. Because the ozone layer blocks or absorbs all the UVC, we don't actually experience UVC on our planet. So there's very few applications for UVC in sensors, so they're very few and far between. There is one source of UVC, and that is arc welding. And that is actually why when arc welding, there's this huge face shield and gloves and everything else. It's actually because of the UVC, not necessarily because of the sparks or the hot metal or anything. That's nothing compared to the UVC. So the thing is that, yeah, it's going to be really, we've got this opportunity actually for some of the students to build their own UVC sensor. So that is definitely going to be something that we're going to want to sense. So yeah, that is definitely something. When one conducts a high altitude balloon mission, one goes to 35 kilometers in altitude with these usual weather balloons. And when the kit goes through, and when this light sensor goes through those layers, it's absolutely incredible how much the UV just, it just explodes. Absolutely amazing. One can actually see that it's going through the ozone layer because suddenly it's being exposed to so much more UVB through the ozone layer. So yeah, that's absolutely great. Anybody else have any more questions? Okay, what I'd like to do is I'd like to go on to our topic for today, which is comfort levels. So for this, what we do is we specifically focus on the weather sensor, because the weather sensor is giving us air temperature and relative humidity. So why is this combination interesting? And also on the back of the chip, what we have is this relates to Sustainable Development Goal number 3, and that is good health and well-being. And it's all because of this. Comfort levels. As living creatures, even as we know with plants and animal life, We are only comfortable under certain conditions of not only temperature, but also humidity, relative humidity. It really comes to the fore when we need to live in habitats, when we're in space. So we're living in an orbiting habitat like a space station, when we're traveling on a spaceship. What we need to make sure of is that we are comfortable. As I mentioned, it relates to goal number 3, Sustainable Development Goal number 3, good health and well-being. And also in this experiment, we will see how comfortable our own living conditions are, and compare these conditions to those of the team actually living on Antarctica. South Africa has a base on Antarctica by the name of Sania, and the engineers have taken a number of these kits and they have them connected to the dashboard. And so what they do is that they actually collect data so that all of the students all over the world can see the conditions that they're living in. So primarily what it is it's around heat index. When we take, there's like this huge formula, which I'm not going to share on the slides because it just doesn't make much sense at all, but I certainly do have it in the assignment. But there's this very large calculation, this equation regarding and where we use temperature and we use relative humidity. And here what we get is we get the heat index and how comfortable are we or how uncomfortable are we. And we can also see here that there's a difference between summer and winter. So let's actually go to this. Let's go to this one here where we have a look at the heat index. So if we have a look at the generic levels, is that living organisms can tolerate ranges of temperature and air humidity only to a certain point. And so what it is that the heat index, when we calculate the heat index, and this is also this is represented as degrees. And I'm so sorry, I'm only using degrees centigrade here because we have the sensors in degrees centigrade, and these are the units that we're going to be using when we work with anything in space. Because the Any Space program is a global program, we stick to the metric. So if we have a look here, anything with a heat index less than 30 degrees, there's absolutely no discomfort. From 30 to 40 is some discomfort, 40 to 45 great discomfort, and then it becomes dangerous, and then beyond 54, then we start getting into the zone of heat stroke and maybe even death. So the purple lines are the most comfortable and the yellow lines are the least comfortable. So are there any questions on that just yet? Okay. What I'd like to do is, before I go there, I actually want to focus on this graph here on the right-hand side. What we can see is that we're also very seasonal creatures. Because our planet has seasons, we're very seasonal creatures. So what we find is that during the summer months, we're very happy with warmer and drier temperatures. That is why a lot of people prefer, in a way, California to maybe perhaps Florida during summer, is because California has got drier summers and wetter winters because there's a Mediterranean climate there. And we have exactly the same here in Cape Town, where I am, very close to the southern tip of Africa, is that we also have this Mediterranean climate where we have dry summers and wetter winters. So the thing is that we prefer it to be drier and warmer during summer, and we really want it actually to be more moist when it's colder. And because the thing is that the moisture in the air actually can contain some of the heat. Otherwise, the thing is, as you experience when it's too dry. For example, when it's too cold and all of the moisture has just frozen out of the air, everything just begins to crack and we become unbelievably uncomfortable. And it's actually very difficult to get warm because it's very difficult to warm the air because there's no moisture to retain the heat in the air. So bear that in mind, because when we do the experiment, or when the students do the experiment later, what they're going to be doing is they're going to be plotting the different rooms and the different areas on this map in terms of using the weather sensor, in terms of relative humidity and temperature. And here with this graph, I asked the graphic artist to put in the Fahrenheit as well, because yeah, it also just needs to make sense to everybody what it is, and not just merely be a number. So if we go to the habitats on Antarctica and we actually have a look at what they're experiencing, they're experiencing temperatures between 10 and 17 degrees centigrade, which is cold. This is inside the habitat. If we have a look at the date, this is pretty important because this is around about April the 3rd, when this data was collected, to July the 25th. So this is Southern Hemisphere, Antarctica, Southern Hemisphere during July, midwinter. So inside the habitat, they were keeping it around about 10 to 17 degrees, which is very okay during winter. Let's go back to, we'll have a look in a minute actually. And then relative humidity, unbelievably dry, 10 to 20%. This is like, and they actually refer to Antarctica as an ice desert because it's so dry. If we go to the next slide and we now plot it on that graph, we can see that they are way out of the comfort zone because it's cold and it's very, very, very dry. So they find it very difficult to, it doesn't matter how many humidifiers they try in that habitat, you know, because I mean, it's not completely sealed. It's not like a space station. And so they find it very, very difficult to get comfortable in that habitat. And, you know, in summer, you know, it gets a little bit warmer, but, you know, the thing is, it's never beach weather. So, yeah, okay, Dave needed to run. That was absolutely great. That's fine. Jim, it's going to be up to you to relay the messages, and I'm sure that you're very, very happy with that.
Oh yeah, will do.
Absolutely. So the activity that we'll be posting later for students is using your weather station, measure the temperature and relative humidity in as many rooms as possible. Plot your findings on the comfort